Hello everyone, we're going to start our unit on thermochemistry with some notes. So, thermochemistry, this is a study of the heat changes that occur during a chemical reaction. All right, and as you know from the lab that we did to start this off, different kinds of chemical reactions will give off different kinds of heat or absorb heat at different levels. So we're going to learn a little bit about all that. Let's start off with some definitions. So energy. Energy is the capacity or the ability for a system to do work or to supply heat. All right. And this concept of work is actually something that you get to more in physics than in chemistry, but we put it out here because it's part of the definition. Energy is something that is weightless, colorless, odorless. You can't see it, but you can tell its effects. Energy stored in chemical bonds is the kind that, of course, we care about here in chemistry. That's the energy of a chemical bond, and it is called chemical potential energy. An example of a compound that has a whole lot of energy or chemical potential energy in its bonds is something like gasoline. When you burn gasoline, you get a whole lot of energy out of it because the bonds that hold gasoline molecule together have a lot of energy stored as chemical potential energy. All right. So this concept of work is where a force is used to move an object. That's kind of something we're familiar with. It doesn't apply as much to chemistry, like I said, as it does to physics. Heat is a type of energy that's transferred, is the type of energy where it's transferred from one object to another because of a difference in temperature. All right, and we have a term that we use to measure heat. It's called Q, lowercase q. So Q is heat, and that is energy that's transferred from one object to another due to a difference in temperature. Now, neither our senses or the instruments that we create can't actually detect heat. We can only detect changes that are caused by heat. All right, so we can detect the change in temperature, which is caused by heat moving from one place to another, but we can't detect the heat itself. And this is probably something you kind of know intuitively, but well, write it down anyway. Heat flows from a warm place to a cold place until equilibrium is reached. Equilibrium just means balance. So heat, like when you've got your hands are cold and you hold them in front of the warm air heater that you have in your, the vent in your living room, blowing out warm air. Your hands warm up because they gain heat from the warm air that's blowing out of the vent. And your hands will continue to get warm until they are the same temperature as the air that's blowing out of the vent. That's an equilibrium. So that's just a little sort of visualization of what I mean when I say equilibrium, a balance. So with heat and temperature, we're talking about flows of energy. And we have to define some terminology about energy flow so that we can discuss things properly. We divide the entire universe, if you will, into three parts. The system, which is the piece that you care about. Maybe that's the chemical reaction happening in your beaker. And then there are surroundings, which is everything else except the chemical reaction going on in your beaker, for example. And then the universe is the combination of these two things, the system and the surroundings. All right, so these concepts are important when we try to define where energy is moving. When we describe or we talk about the flow of heat, when heat flows into a system, for example, that beaker sitting on the countertop, maybe that's where your reaction is going on. If heat flows into a system, it's called an endothermic process. Endo means inside and thermic refers to heat. So this means endothermic means taking in heat. So heat flows in, that's an endothermic process. And when we do calculations, by convention, an endothermic process is shown with a positive Q. So energy is coming into the system, and that's a gain of energy or of heat, and so we show it as a positive Q. If heat is flowing out of a system, so that like a reaction is going and it's giving off heat, like the combustion of gasoline, for example, definitely gives off heat, that's an exothermic process. That means heat's flowing out of the system. It's giving off heat. We show that Q as a negative Q. All right? A couple more definitions we need to go through. A calorie. So we talk about calories in diet, right? And how many calories are in that cheeseburger you ate, that kind of thing. This is a different kind of calorie. It's a smaller calorie. The calorie in the dietary world is actually a kilocalorie, or 1,000 of these kinds of calorie. So I hope that that doesn't get confusing. When we talk about calories in chemistry, we're talking about the quantity of heat required to raise 1 gram of water by 1 degree C. That's the definition of a calorie. All right, and we measure calories in we measure heat in joules. So that's another. So one kind of unit is a calorie, another kind of unit is a joule, and they are connected to each other. This is just like those atmospheres, torrs, atmosphere torr, kilopascals, and so on that we use to measure pressure. We have a couple ways of measuring heat. One is the joule, one is the calorie, and they're connected to each other by this equality. All right. So, but the definition of a joule, of a calorie is given here: the quantity of heat required to raise 1 gram of water by 1 degree C. So that's the definition of a calorie. There's a concept called heat capacity, and this is how much heat an object can absorb, basically. We define this as the amount of heat needed to raise the temperature of an object or a compound by 1 degree C. So it kind of is, it sounds a little bit similar to that definition for calorie that we had, but notice the important difference. This is the amount of heat needed to raise just the temperature of an object. We're not talking about any specific object or any specific compound. The amount of heat needed to raise the temperature of an object by 1 degree C. So heat capacity, this number, this characteristic, depends on the mass and the composition of the object. So the heat capacity for 10 grams of lead is different than the heat capacity of 1 gram of lead. Now, if you think about it, that just makes sense, because heat capacity is how much heat you have to add to something to raise its temperature by a degree. Well, if you've got 10 grams of something, it's going to require more energy to raise that temperature than if you had 1 gram of something. So hopefully that kind of makes sense. We do have a measurement that is independent of mass, which is important. So we have something called the specific heat, or specific heat capacity. All right, and this is defined as the amount of heat it takes to raise 1 gram of a substance by 1 degree. 1 gram of a substance by 1 degree, that's its specific heat capacity. And this is this variable is shown by the capital letter C. So, of course, we have a calculation, because we like to do calculations in chemistry, and this is one that ties these concepts together. So here, capital C is our specific heat capacity, which, again, is the amount of heat it takes to raise 1 gram of a substance by 1 degree. And this is measured in joules, which is our energy measurement, per gram degree C, or calories per gram degree C, because remember, there are 2 ways to measure heat, either in joules or in calories. All right, so if we look at this equation that we've got, Q equals C m delta T, C times m times delta T, where C is the specific heat capacity, Q is the heat in joules or in calories, m is a mass in grams, and delta T is the change in temperature, not the actual temperature, but the change in temperature. All that matters is the T final minus T initial. That's what delta T equals. All right? And you can use this equation to do calculations with heat, which we will see in our sample problem. So here's one starting point sample problem. If you have, when 435 joules of heat is added to 3.4 grams of olive oil that start at 21 degrees C, the temperature increases to 85 degrees C. What is the specific heat of olive oil? Okay, let's think about that. Let's take a look at this paragraph first and see what we can kind of figure out. We know that heat is measured in joules or in calories, so this is a heat term, and if you remember, heat is abbreviated with the letter Q. Is added to 3.4 grams. That sounds like a mass, so here's M. Here's a temperature, and here's a temperature, and but we don't want actual temperatures, we want the change in temperature. So delta T is T final minus T initial, so 85 minus 21, and I have some of that laid out here. What we're trying to find is the specific heat of olive oil, which was that capital C. So we don't know what that is, but we do know Q, we do know M, and we do know delta T. And that means we can use our equation Q equals C m delta T. So I just had to repeat that information so that we could fit it onto the slide. Let's rearrange that equation to solve for C. You get C equals Q over M delta T. So C equals Q over M times delta T. Let's substitute numbers in there. C equals 435 joules divided by 3.4 grams times 64 degrees. Where'd the 64 degrees come from? Well, remember, delta T is T final minus T initial, which is 85 minus 21, which equals 64. So you do this math and you should get 2.0 joules per gram degree C. If you remember from a couple slides back, the units for specific heat or specific heat capacity are joules over gram degree C. So that looks like we set it up right. There's our answer. Here's another sample problem. How much heat is required to raise the temperature of 250 grams of mercury by 52 degrees C? And it tells us the specific heat of mercury is 0.14 joules per gram degree C. Okay, so again, we got to parse the problem, figure out what we know, what we're trying to find. We're trying to find, it says how much heat, if you remember, this is Q. So we're trying to find Q to raise the temperature of 250 grams. That sounds like a mass, right? So there's our mass, M. And we have our specific heat, which is capital C, that's 0.14 joules per gram degree C. The other number we have in this paragraph is by 52 degrees C. So this is the change, that's why this one is a little bit trickier. This is our change in temperature right here. We're not given a starting point and an ending point for temperature. You're just told that the temperature goes up by 52 degrees. So that means delta T is 52 degrees. Does that make sense? Make sure you write that down as a question for tomorrow if it doesn't make sense. Here's our equation. C, we know what that is now, 0.14. We're trying to find Q. We have our mass. We have our delta T. We're going to use this equation. Q equals C M delta T. And so we substitute 0.14, 250, 52. Do the math, and you get 1,800 joules is the amount of heat required to raise the temperature of 250 grams of mercury by 52 degrees. Now, thing that's kind of interesting to note, it doesn't tell you that, well, this amount is the same whether your mercury is going from 100 to 152 degrees, or if your mercury starts at 500 and goes to 552 degrees. The amount of heat required to raise that temperature by this amount is the same, regardless of your starting or ending points. All right, that's it for now. So bring your questions tomorrow. We'll work some sample problems. It'll be very exciting.